So I'll just be giving an introduction on the vehicle autonomy stack and what are the different components that are required for or to lead towards a fully autonomous vehicle. So to begin with, let's look at what we have been envisioning in terms of an autonomous vehicle, intelligent vehicle future. We are often shown pictures of this kind where we see like a utopian city with futuristic looking self-driving vehicles navigating through crowded city streets with many different participants, which are vehicle and non-vehicle, so pedestrians, bicyclists, two-wheelers, etc. And these are some of the things that we have been promised over the past decades. So famous people working at or heading big companies, and they say self-driving cars are a natural extension of active safety and obviously something we should do. And then we see the CEO of a leading self-driving car company saying that vehicles will be self-driving, so you'll have your own personal space where you can sit back and relax. And we see the CEO of one of the leading automotive giants say that we can very soon expect high volume auto manufacturers to have fully autonomous vehicles. We see promises of level 4 autonomous vehicles by 2021 with no gas pedals, steering wheels, etc. We have been promised about 10 different self-driving cars within a single company's umbrella by 2020. But obviously, these promises or visions have not completely materialized so far. And my talk today is aimed to kind of look into a bit of why is this not happened yet? What are the different challenges, and what are some of the state of the art and leading directions in which developments are taking place to realize this fully autonomous future. So just as an introduction to vehicle autonomy, so how is vehicle autonomy defined? So the Society of Automotive Engineers defines vehicle autonomy on 6 different levels. So level 0 is the vehicle you see at the bottom here, which is no autonomy. So it's a normally human driven vehicle that you see at the bottom. Then you have level 1 autonomous vehicles, so where they have basic driver assistance systems like anti-lock braking systems or ESP systems, cruise control, etc. Then you have level 2, where vehicles can accelerate on their own in limited conditions, or in controlled environments they can steer themselves or brake themselves without any human intervention, but they still need to be monitored. We have level 3 vehicles where the driver doesn't need to keep eyes on the road most of the time, but only in certain situations they can take their eyes off the road. Then you have level 4 vehicles where the autonomous vehicle can drive itself in almost all the situations. And then finally, level 5, which is the future that we see, which will be a fully autonomous vehicle, no driver intervention required. You don't need steering wheel, acceleration, brake, any of such pedals. So you just go there and sit. So far in the mass production vehicles, we see level 2 vehicles from quite a few manufacturers, but nothing beyond. There are a few vehicles in mass production today which you can actually buy off showrooms, which can do level 3 autonomy in very select scenarios. However, everything 3 and beyond is still not completely achieved in all real world driving scenarios. So, but the eventual goal, as I mentioned, is to reach level 5 autonomy. Expanding a bit further into level 5 autonomy. So what does a vehicle need to do level 5 autonomy? So if it is a vehicle capable of doing level 5 autonomy, it's essentially a robot that is intelligent enough to discern the environment, make decisions, and then actually take those decisions or perform those decisions. So there is something called as a vehicle autonomy stack that is used to develop this capability for a vehicle. So on the top level, you have the sensing. So that's what so the vehicle is basically just a robot, and it has to sense the environment. So it has a different host of sensors around it. It's connected to the internet, and that forms its a sensing suite that's used to get some kind of an environmental perception. So that's the second level of the autonomy stack. And the environmental perception is to understand or make sense out of the raw data that you get from the sensor and convert it into some realistic environmental description. Based on this perception of the immediate environment, the vehicle plans its path in the immediate vicinity. Should it accelerate? Should it brake? How much steering action should be provided, etc. And once the path is planned, the vehicle has to actually control it. So it has to control the steering, the wheels, the acceleration, brake, etc. to actually follow this path that was planned. So that's the fourth level of the vehicle autonomy. And finally, we have the actuation layer. So where the actual hardware components are actuated. So you might have your electric motor or the internal combustion engine. You have the brakes. You have the different differentials. So all of these need to be actuated to actually track the path. So this entire suite is called the vehicle autonomy stack. And basically any vehicle that is capable of level 5 autonomy will require robust and completely developed capabilities at all levels of this stack. So just moving ahead, just now a brief outline on what I'll be talking about. So I'll be going through the autonomy stack that I just introduced. So sensing, perception, path planning, path tracking, and actuation. I will talk a bit in more detail on path planning and path tracking, but that's not because it's more important than sensing, perception, and actuation, but it's a bit more focus of my research, and I can probably share some more details about it. And finally, I'll be laying out some future career prospects that we have in this field of vehicle autonomy. So there's always already a mature field in automotive systems, but now with this advent of autonomous vehicles, there are a host of new career paths that are available. So I'll just be giving a brief introduction about the career prospects. So let's dive straight into the topic. So to begin with, let's look at vehicles sensing system. So what you have here is the top view of a vehicle that is currently available in mass production. So you can actually buy it off the of a showroom. And what I've tried to show here is the actual vehicle sensor suite that it is provided with. So you have multi-mode radars, you have stereo cameras, you have long-range radar, and you have ultrasonic sensors. And I've color coded them so that you can easily see what is the difference between these sensors. So we can see the long-range radar can look up to 250 meters in front of the vehicle, but it has a very, very narrow field of view. Then you have a stereo camera that can look up to 90 meters in front of the vehicle, has a wider field of view. Then you have shorter ultrasonic sensors with short range that can look in the immediate vicinity of the vehicle. So just to see who's in the next lane, who are in the blind spots. And then at the back, you have another set of radars with medium to high range and wider field of views. So this is what we have in a typical high-end production vehicle. And using this, the vehicle tries to understand what is around it, and then it has to perceive the environment and proceed down the autonomy stack. So as you can see, the vehicle cannot actually see 360 degrees around itself. And also, as very evident from the picture, you can see that all the sensors have different fields of view, different capabilities, and the vehicle needs to kind of use these host of sensors to fill in the gaps in knowledge and also proceed with the perception. So just looking forward, so what are the different kinds of sensors that we have in the vehicle? As I already mentioned, you can see the radar, camera, ultrasonic sensors, etc. So their main task is to discern the dynamic environment that you have around the vehicle and make sense out of it. Now with this host of different sensors, radar, camera, etc., each has their own characteristics in terms of range, which operating regimes they can work in, how accurate they are, etc. So on the top figure here, we have a comparison between two sensors that are very commonly used for the next generation of autonomous vehicles. One is a LiDAR and you have a radar. So LiDAR is a kind of a sensor where the sensor itself shoots out particles of light. These particles of light bounce off obstacles and then are received back by the vehicle. And based on the reflection pattern, it tries to understand where the obstacles are. Radar is also a similar kind of technology but uses a different electromagnetic spectrum. And what we see is in the black, you have the characteristics of a perfect LiDAR sensor. So you see it has very good field of view, very high range, good accuracy, frame rate, etc. But that's for a perfect sensor. And then what you can actually achieve in real world is something called as a rotating LiDAR. So it kind of is sitting on top of the vehicle and it's rotating, so it gets a 360-degree view. And we see that it has very high price, good visibility, good field of view, but actually the frame rates and resolutions are not very similar or not what are promised by the perfect sensor. And then you have a solid state radar, which has slightly different characteristics. Moving to a radar, we see a perfect sensor because it is based on the same fundamental technology as a LiDAR. The perfect sensor has the same characteristics, but a real world radar gives us quite something else. So it has a different set of compromises to be made. Moving to cameras, again, you have a perfect sensor, which again, because it's looking at electromagnetic radiation, has the same characteristics for a perfect sensor, but we see the real world sensors based on infrared or time of flight sensors, slightly different characteristics. And we can do a comparison between these sensors to come up with a strategy of which sensor to be mounted on which part of the vehicle and actually what is the purpose of this sensor. However, as I've just explained, we have some characteristics of the perfect sensor and a real world implementation. So there needs to be a balance between price, what range you get, accuracy, how much data you are generating, etc. So this is a brief introduction on the sensing suite of the vehicle. So as one of the main conclusions that we can draw from this is that a single sensor or single type of sensor is not sufficient for any vehicle. We need to have an entire sensor suite to perform different tasks, and these tasks or these outputs are then combined to actually get a more holistic or realistic environmental perception. So these same sensor characteristics can be used to compare what are the capabilities of these sensors in terms of vehicle perception. So the characteristics were more a bit on the technical side of any sensor characteristics, but we can also translate them to capabilities that are relevant for autonomous driving. So for example, with the camera, we see that we can get good range and resolution, but it obviously doesn't work in the dark. It doesn't work when there are bright sources of light in front of it. So if the sun is shining directly into the sensor, or you have some reflections, doesn't work well in snow, fog, rain, but it can provide good color contrast. Cannot be used to detect the speed of the obstacle. So it cannot understand that which obstacle is a building or a stationary member of the road. So something like a post or some parked vehicle, and it cannot understand which is a moving vehicle. The sensor's size is quite small, and because of the high level of maturity in the field, the sensor is economically very viable. When we look at the LiDAR, it again has very good range and resolution. It can work in the dark. And that's because the camera is basically relying on external light sources to illuminate the obstacles, whereas the LiDAR shoots its own light. So whether the outside environment has light or not, it can still work in the light. It can work in the high brightness, but again, it struggles a bit in snow and fog. Cannot really provide good color contrast, but it can be used to detect the speed of the obstacles. The sensor size is not really currently in a state that it is very beneficial. So that's why when you see the prototypes of autonomous vehicles, you see big sensors or big LiDAR arrays mounted on top of the vehicles, which actually cannot go into production because you need something that is seamlessly integrated. And also another thing is the cost of the LiDAR. LiDAR sensors are extremely expensive. So a single LiDAR sensor might cost as much as an entire vehicle. So obviously, it's still not in a stage where you can have it readily available in production vehicles. Moving to radar, again, we have good range, resolution. Resolution is not so good, but it works very well in dark, works in bright conditions, works in snow, rain. Not really good at providing contrast, but you can use it to detect the speed. And as you know, radars are used very often for cruise control systems in vehicle, where the vehicle tries to maintain a safe distance to a vehicle, and it does that by detecting the speed of the obstacle. Radar sensors have matured greatly over the last few decades, and so the sensor size and sensor cost are no longer a problem for automotive, because you can get them for very economical prices. So this picture gives a bit more idea of why we need a host of sensors, because an autonomous vehicle is not only going to work in perfect sunny conditions during the day, but also in night, in strange lighting conditions, in fog, rain, and different weather conditions. It has to detect speed. It has to be economically viable. So you cannot have a vehicle with 10 LiDAR systems. Similarly, you cannot have a vehicle with just radar to look around, or just a camera. So the company needs to make a smart decision on how to have a balanced suite of sensors that can be used to get a good environmental perception. So moving ahead, what are the what actual information do you derive from all these sensors? And that is actually the crux of the perception. So you actually, using the data that you get from the sensors, you can detect objects and identify them. So you can see whether it's a pedestrian, a traffic, what kind of a vehicle, is it standstill, etc. You can do some kind of motion prediction. So the vehicles in your immediate vicinity, you can try to predict if they are going to take a turn, slow down, continue on their current path, etc. And basically, using these first 2 points of information, the autonomous vehicle is expected to somehow compute the safe driving corridors around it, so which are the safe and unsafe regions around it, and use those to make decisions on what kind of maneuvers it can perform. So here I have just put screenshots of actually what a camera system in a vehicle can see. So a camera system sees something very similar to what a human eye sees. The ultrasonic sensor is, as I explained, a short range sensor, so it can only look at obstacles which are very, very close to it, so very useful for parking. Then you have a long range radar in the front bumper that is looking straight ahead, so it can understand what is in the road. And then you have the LiDAR. So you see all these dots around the host vehicle and can kind of look or make a 3D map of, or technically it's called a point cloud of the region around the vehicle. And the actual output of that is something like this. So the camera will get these obstacles or what you see in the top plot here. So it can actually find out which are the pedestrians and mark them. Similar camera system can mark out the obstacles as in vehicles, and then combining this LiDAR and radar information and with the camera, output of the perception is something that you see here. So all the obstacle vehicles are marked in pink. The unsafe lanes, with the degree of or how unsafe they are marked in different shades of orange or red. And what the vehicle sees right in front of it, it has marked as a safe corridor, so which is in green. And then the output of the perception block would be some information like this, where the vehicle understands, okay, this green region is the only region that I can drive along, and then it will try to come up with a path to drive in this region. And I just want to mention this, that this object detection, identification, motion prediction, etc. has to happen continuously, because the environment around the vehicle is very dynamic. So this will probably be happening 20 to 50 times a single second. So this is kind of a brief introduction on what the perception happens. So at the end of the perception, the vehicle has a reasonably accurate representation or awareness of the situation around it. It knows what is risky, what is not risky, and it knows where it can go and where it cannot go. And that brings us to the next part, that is path planning. So once the vehicle knows what is the situation around it, it has to actually plan a path. So path planning, you can kind of define it as the vehicle's transition from one feasible state. So you can see here it's right now in this state where it's behind a vehicle and there is another vehicle in the other lane. And so that would be a transition from this blue dot to, it has to come up with a reasonable transition in the next lane. And it has to do this transition while satisfying the vehicle's its own kinematic and dynamic limits. So in terms of how much acceleration it can input, what kind of steering angles it can provide, how fast it can brake, etc. And it has also to take care of the occupant's comfort, the lane boundaries, so it has to respect the rules of the road. It has to also, most importantly, avoid all obstacles. So while transitioning from, for example, here one lane to the another, it shouldn't hit any obstacle, jeopardizing the safety of the entire exercise. So that's path planning in a very short gist. But as you can see, it's not a very trivial challenge. So we have to consider vehicle dynamics. You have to consider the driving behavior, not only of your own vehicle, but also the vehicle that are in the vicinity. The autonomous vehicle has to consider all the safety margins. And this algorithm that will be actually used for path planning has to be real-time applicable. So an autonomous vehicle might not have very high computing platforms available to it. So it will not have a desktop computer running on it. So the algorithm that one designs has to be capable of running on maybe low powered ECUs or medium powered computing platforms. And it has to happen 20 to 100 times a second. So it should be real time applicable. The trajectory that is planned should be feasible, so it should come up with a path that a vehicle can actually follow and not just any path. And it should be, and this entire algorithm for path planning should be robust against system non-linearities, external disturbances. So you might have wind blowing across the road, you might have patches of ice and snow, you might have some unforeseen circumstances, someone running across the road, and the algorithm should kind of be robust against all of this. And obviously, it's quite a big challenge to have a single architecture that can address all these challenges and do them for every single maneuver that a vehicle has to perform. So that would be lane keeping, accelerating, braking, lane change, exiting highways, entering highways, taking blind corners inside within city streets, navigating through tunnels, reading road signs, etc. So it's quite a big challenge. So in path planning, there are quite a few approaches that are available. I cannot really go into the techniques used or designed by individual companies because they are often IP protected. So the intellectual property rights of them are protected. So it's not really available in public domain, but broadly give an introduction of the different techniques that are usually used for path planning in autonomous vehicles. So the first type of path planning is something called as a grid-based search, where what happens is that space around the vehicle, so the physical space, which is the XY coordinates, transformed into a configuration space. So what I mean by configuration space is the XY coordinates are transformed into the different configurations that a vehicle can take. So it can be at position 0, 0 in a certain pointing in a certain direction. So if you have a grid of 100 points around the vehicle, you can have a configuration space for each grid point in terms of what position or pose the vehicle can be. And how the algorithm tries to operate is, so you have the source grid point and the destination grid point, and it tries to come up with a shortest collision free path from the source to destination. So I have a few examples here. So you have on the right a very famous algorithm called Dijkstra's algorithm, and on the left you have something called as an A star. And you can see these algorithms in action. So we have the source over here where my mouse pointer is, and the destination here, and you have like just a sample environment. So these black lines are obstacles or points which the vehicle cannot cross. And then you see how these two different algorithms behave. So the A star algorithm kind of is designed in such a way that it searches in the general direction of the obstacle. So you see the path searched go in this direction, and then it goes up here, then it immediately crosses over here, but because of the obstacle, then it has to overlap, and then it finds the path. In contrast, what the Dijkstra's algorithm you see here does is it kind of searches for all configuration spaces in the immediate neighborhood and then keeps expanding, kind of expands in a spherical way. So these are two very famous grid-based search algorithms. What I've shown here are the most basic versions of them, and they are heavily used in the autonomous robotics industry. So they've been used for a long time. They are very mature. And there have been a lot of enhancements in these grid-based search algorithms to compute collision-free path. There's also a few more techniques for path planning based on grid-based search, and there's something called as a potential field algorithm. What happens there is that the grid, so the x-axis and the y-axis, and you have the source or the source point here and the destination. And what you have in the spheres here are the obstacles. And the task of the autonomous system is to navigate from the source to the destination while not hitting the obstacles but finding the shortest path. So how you can do that is you can define the entire space in terms of an artificial potential. So you say that the destination is at the lowest potential, so it has the lightest color, and the source or the origin point is at the highest potential. And you have to design a search algorithm that you basically come up with search that finds the shortest path from highest potential to lowest potential while not hitting any obstacle. So it basically some kind of a search algorithm, and there are many search algorithms available. And this is also quite often used in autonomous robots to come up with collision free paths. And the challenge is to kind of import these grid-based search algorithms and use them in the autonomous vehicles context, ensuring that all the rules and constraints of the autonomous vehicle that I discussed in the previous slide are respected.